Lambda in the sense wavelength. Lambda by 4 is quarter wavelength. Lambda by 2 is half wavelength. And it is lambda by 8. Lines in the sense transmission lines. So we will see the first one. These are very easy. Just we need to calculate the input impedance for the transmission line having a length of lambda by 4. That's it. So lambda by 4 transmission line, the first one. Just draw a two-wire line. Okay. And at the input, please connect to the source. Other end connected to load. So just I am telling you that the length of the transmission line is lambda by 4. And the characteristic impedance of the transmission line is Z0. Diagram clear?
Yes, sir.
Now we find the input impedance for this quarter wavelength. We say it as a quarter wavelength transmission line. Now Zin formula, again going for the case of a lossless transmission line, recollecting it, ZL plus JZ0 and beta L by Z0 plus JZL and beta L for lossless transmission line. Now, tell me what is this lambda by 4? L, am I right? The length of the transmission line, L, is lambda by 4. Now what happens to beta L now? Beta is 2 pi by lambda into L is lambda by 4.
Pi by 2.
Yes. So therefore beta L will be pi by 2. So simply go for substituting that pi by 2 in Zin formula. What happens? What happens to tan of pi by 2?
Infinity.
Infinity. I can't directly write infinity, right? So what I am doing is, dealing with infinity, we will generally divide with the term which is becoming infinity. So just dividing the numerator and denominator with tan beta, because it is becoming infinity. Clear till this point?
Yes, sir.
And now substitute beta L pi by 2. What happens to Zin in this case? This becomes 0 plus JZ0 by, again this becomes 0 plus JZL. So Zin, in the case of a quarter wavelength transmission line, can cancel that, Z0 square by ZL. Okay. From this, you can derive one formula that Z0 square equal to Zn into ZL. For a quarter wavelength transmission line, you can calculate the characteristic impedance by simply taking a root for the product of load and the input impedance. Right? Shall I proceed for the next length?
Yes, sir. Yes, sir.
Next is half wavelength, lambda by 2 transmission line. The same process that you can do now. Same process. Just take a transmission line, two-wire line, connect to the load on one end, connect to the source on other end. Length of the transmission line is now lambda by 2, and we are now trying to find the input impedance. So now L is lambda by 2. What happens to beta L? Check. Yes, what happens? Then what happens to tan beta L in this case?
Pi. It will be 0.
0, right. Tan beta L 0. Now it has been simplified. So Zin for a lossless transmission line. Just write the formula. ZL plus JZ naught tan beta L by Z naught plus JZL tan beta L. So tan beta L is 0. Therefore, Zin in this case will be Z naught into ZL by Z naught. And finally, we got a case that Zn equal to Zl. Any conclusion from this? Any conclusion from this? Okay, let me tell you. A transmission line which is connected to load on one end and source on the other end, and if you observe that the length of a transmission line is half wavelength, where Zn you have calculated and got it as same ZL. This is equivalent to directly the source is connected to load without any transmission line. Since ZL is Zn equal to ZL in this case, this transmission line can be neglected, and that is equivalent to directly source connected to load. Clear? Because they are equal, when the length is lambda by 2, it is equivalent to source directly connected to load. So you may ask, sir, so what happens then? Then why there is need, use of this half wavelength transmission? I'll tell you one application. Just assume that there is a transmission line. Maybe I'm drawing the diagrams repeatedly same, but they're repeated. And the transmission line is connected to the load, right? And I say that the length of a transmission line is L plus not only lambda by 2, not only lambda by 2, you can write in general that when this L is n times lambda by 2, this is true. Zn is equal to Zn. So L plus, whenever I find that the length of a transmission line is some L plus n lambda by 2, then I can equivalently represent that as a transmission line having a length only L connected to load on one side and source on the other side. Clear enough? Yes, I want to get a clarity from your side.
Yes, sir.
So this half wavelength transmission line concept can be used to reduce the length of a transmission line so that we can reduce the amount that we spend on a length of a transmission line. That means I can reduce such length when it is n lambda by 2. So when the transmission line is some L plus n lambda by 2, then this length need not be in physical connected. Just a length of L can be enough to say that the load, the source is connected to load properly. That means you can neglect this L. That is, you are saving resources of a length of n lambda by 2 without expending money on this. You can simply go for a L. So this half wavelength transmission line concept is used to reduce the length of a transmission line. If it is only half wavelength, then transmission line is not required. It is directly equivalent to directly source connected to load. If it is L plus n times half wavelength, then it is equivalent to the transmission line which is having a length L, because in this case Zn is equal to Zl. Okay, clear? That means here if I measure the input impedance, this will be like this. That's why we remove this n lambda by 2. What is the third one? Can you please do the third one and tell me what happens? Meanwhile, I will draw. ZL, source impedance, and the source. Now, what is L? Now, what happens to beta? Beta L? What is beta L now?
Lambda by 4.
Right. It is lambda by 4. So when lambda beta L is pi by 4, what happens to tan beta L?
1.
Right. Tan of pi by 4 is 1. Now please again recalculate the input impedance for this transmission line having a length of lambda by 8. Z0 into ZL plus JZ0 tan beta L by Z0 plus JZL tan beta L. So tan beta, this is for a lossless transmission line, once again mentioning, and this is tan beta L becomes 1, so you'll get Z0 into
ZL plus JZ0 by Z0 plus JZL.
right. Okay, now since I'm mentioning that it is a lossless transmission line, can you please tell me what is Z0 for a lossless transmission? We did two cases. One lossless transmission line, the other one is a what I said, distortionless transmission line. So for lossless transmission line, can you please tell me what is Z0? Just check your book and tell me.
Under root of LC.
Right. So it is a constant now. It is a real.
Yes.
It is a real constant. Okay. Am I right? Am I right or wrong? Z0 is a real function, right now, real value. So in this case, when I calculate mod, that is taking its magnitude of Zn, then it becomes mod Z0 into, and assuming that ZL is also real, just I am assuming that ZL is also real. Now what happens to this mod ZL plus JZ0 by Z0 plus JZL? Anyone? For lossless transmission line, Z0 is already a real function. Just I am assuming that ZL is also real. What happens to mod ZL? Mod is Z0 is a real function, so no need to write mod. Okay. Tell me, root over real part square plus imaginary part square by root over. Can you see they get cancelled? So mod Zn is equal to mod Z0. In this case, when I am talking about a Z0 for a lossless transmission is already real constant, and based on the assumption that Z0 ZL is real. Okay. Now just assume that ZL is purely imaginary. ZL is purely imaginary. Now what happens? What happens to this Zn now? Tell me fast. Can I write like this as JXL, purely imaginary?
Yes.
Since we know that ZL is equal to R L plus JXL, I am saying that it is purely imaginary. So R is 0. So please substitute that. Z0 is already real. So it is JXL plus JZ0 by Z0 plus J times JXL. Z0. This can be written as J times by Z0. Yes, you can stop here. It's enough. Like this, you can stop. Okay. Clear this point?
Yes, sir.
Yeah. So just recollecting. We are verifying the input impedance for different transmission lines having different lengths. The first case is quarter wavelength, and we found that the input impedance for a quarter wavelength is Z0 square by ZL, where Z0 is a characteristic impedance and ZL is the load. And from that we derive one more formula that if Zn and ZL are known, then we can easily calculate the characteristic impedance for a quarter wavelength transmission line. Next we took half wavelength transmission line. Again we found the input impedance of a lossless transmission line. It is clear that Zn is equal to ZL. So this result is very interesting, that when I calculate Zin and you got this is equal to ZL, that means that there is no need for a transmission line which is connected. So this is equivalent to directly load source connected to load. So this concept of half wavelength transmission line is used to reduce the length of a transmission line whenever it is required. That means when I use a transmission line having length of some L plus n times lambda by 2, so that n times lambda by 2 length can be removed, and directly it is equivalent to only the length of a transmission line L connected from source to load. This is used in reducing the length of a transmission line. And the last one is lambda by 8 transmission line, and where we observe that for a lossless transmission line, and assuming that ZL is real, you have got that the magnitude of Zin and Z0 are same. Magnitude, I'm talking about magnitude. When it is purely imaginary, you got some expression for Zin, and if it is complex, you can directly use this formula. So all this is an extension. You can stop here actually. When L is lambda by 8, you can stop here, no problem. That is Zn is Z0 times ZL plus JZ0 by Z0 plus JZ. You can stop here. If we want to discuss something more about it, you can talk about the assumptions. Like when for lossless transmission Z0 is already real, then you talk about two cases: when ZL is real, or when ZL is purely imaginary, or ZL is a complex. That is how you can talk about this input impedance for lambda by transmission.